Hello and welcome to Options in Plain English. Today we're going to talk about the most important second-order Greek, gamma. Gamma measures how much delta changes as the underlying price changes. It is a measure of acceleration of profits if you're long gamma and an acceleration of losses if you're short gamma. Gamma is what allows your long options to profit more and more as the stock price goes your way, making your deltas go in the direction of the move. This advantage has a cost though. To enjoy the potential acceleration of profits provided by gamma, you'll have to lose money due to theta if price doesn't move your way, or if it moves against you. We're going to explore this relationship between gamma and theta in this lesson. We'll also isolate the effect of gamma in day-to-day P&L by looking at the delta gamma approximation and focusing on the effect of gamma. This will give you a good perspective as to how gamma is reflected in day-to-day profits and overall profits and losses in general. We're going to start by looking at the Greeks and seeing where gamma is. Gamma is right here. It is the how much delta changes as the underlying price changes. We've already looked at delta, which is the underlying price modifying the option price, so how much the option price changes as the underlying price changes. And also time to expiration affecting the option price by looking at theta. Theta being how much the option price changes as time to expiration passes, typically 1 day. Gamma is a second order Greek and it measures how much delta changes as the underlying price changes. As you can see, gamma is the second derivative of price with respect to underlying price. This is the one that we're going to be looking at in this lesson, and this is the actual definition. Gamma measures the rate of change of delta with respect to changes in the underlying price. Gamma is the second derivative of option price with respect to underlying price. It's also how much will the delta change for every $1 change in the underlying price, assuming that nothing else changes. So that time to expiration doesn't change, strike price, implied volatility, dividends, and interest rates. So if you look at gamma and you compare it to being long and short, a call or a put, you'll notice that when you're long an option, you're going to have positive gamma, regardless of whether you're using a call or a put. When you're short an option, either a call or a put, you're going to be negative or you're going to be short gamma. And long gamma is always a way to make money by having the delta move in the direction of the move. So if you have a call and it has obviously positive gamma and a certain delta, if it starts going your way, meaning the underlying price starts going up, then gamma is you're not going to only enjoy the profits from your delta times the move, but also delta itself is going to go higher as the price goes higher. So when the price is moving in your favor, you start getting more delta so that your profits are accelerating. The same thing happens in the opposite side. If it starts moving against you, then it's going to start decreasing the delta so that move down starts hurting you less and less. So it's always good to have positive gamma, but it has a price, and this is what we're going to see here in this lesson. Gamma is positive for long options and negative for short options. If you think about a long call and you see that you are here at the money and you buy a call, it has a certain delta here, and it starts going your way, you start making money, of course. But if you notice how the curve changes, as it starts moving your way, it starts making more and more money for every unit that the underlying price changes in your favor. So for example, here you can have a delta of around 50, which is at the money. If it starts getting in the money, then let's say, for example, here you have a delta of 70. So for every $1 that the underlying price moves your way, you're going to enjoy 70 cents of profits. But if at that point, probably your delta is going to be 75, let's say. So for the next dollar, you're going to enjoy a profit of 75 cents for every dollar. And then so on and so forth, such that if things start going your way and you start having a lot of success and the price moves in your favor by a lot, at this point you're going to have a delta that's approaching 1. So it's going to start moving 1 to 1 with the underlying. And remember that you started right here, which is with a delta, let's say, of 25 or 30. So you started with 30 and you ended up with almost 1. So with almost 100, it means that from 30 to 100, it was gamma that was changing the delta. Forget about the profits, just focus on the delta. If you have a short call, it's the opposite. When you're here, the at the money, you sell this call. Okay, so you're short a call. At the beginning, it starts losing your money, but at a very slow rate. As the price keeps going against you, the gamma is going to move delta against you as well. So you're going to start losing more and more, such that if you reach a point here where you have a delta of, let's say, minus 80, and then it moves $1 against you, you're going to lose 80 cents or $80 for every dollar that it moved, that the underlying moved against you. But at that point, it's going to have a delta of minus 85 maybe. So for the next dollar, you're going to lose 85 cents. And then for the next one, you're going to lose 89 cents, for example. So the losses keep accelerating, keep snowballing. So this is why the gamma is a measure of acceleration. In this case, for the cases where you're short options, it's an acceleration of losses. And the cases when you're long options, it's an acceleration of profits. If you think about the delta, and this is the graph that we analyzed in the Option Greeks delta lesson, you have something where you have the passage of time reflected in these curves. So you start with the solid one, then you go to the dash one, and then you go to the dotted one. So you see at the beginning, this is the delta, and then the delta starts approaching this line, which is the line at expiration, where this is for a call, for everything that's out of the money, because this is the at the money. For everything that's out of the money, it's going to have a delta of 0, and everything that's in the money is going to have a delta of 1. So prior to expiration, these are the curves as time starts passing, and as the price starts going and moving in your favor, you can see how the delta keeps going higher and higher and higher in your favor. Okay, when there's very little time, then what you're going to notice is that if you're here at the money or near the at the money and you have very little time to go, the delta could switch from, let's say, 20 to 80 with a very small move of the underlying. So this is something that we're going to analyze later on, but that is how gamma acts as time passes, and when gamma is the most when gamma is affecting the delta the most. For put delta, it's exactly the same, just this is a negative axis, so it's minus 20, minus 40, minus 60, etc. As the price starts going your way, you start getting better, more negative deltas. So if you start here, you have this delta, which is probably minus 20, and things start going your way, and you hit the at the money, for example, then at this point you have 50. So you went from 20 negative deltas to 50 negative deltas, which is very good for you if you were long the put. Those profits, now you're not gonna benefit by 20 cents out of every dollar that it moves in your way, but now you're going to benefit by 50 cents for every dollar that it moves your way. This is how gamma is reflected in the graph of delta. Okay, notice how I'm not showing gamma here, I'm just showing delta, but gamma is the reason why delta changes as price changes. So if we start analyzing and we assume that there's no dividends and that the interest rate is zero, just to make the formula easier, gamma is going to be equal to the standard deviation, or to the standard normal distribution of D1 divided by the stock price, implied volatility, and the square root of time. So this is gamma. This is a capital gamma, capital Greek gamma. We also have the lowercase n of D1, lowercase n of D1, which is the standard normal distribution of D1, stock price, implied volatility, time to expiration in years. D1 is calculated this way. It depends on the on where the stock price is in relationship to the strike price, and also R, which in this case is 0, and then implied volatility squared, and then you have implied volatility in here in the denominator. Okay, this is the standard normal distribution. So because this one is here on the top, so on the numerator, you're going to have the basic shape of the bell-shaped, something that's similar to the normal distribution. It's just going to be either taller or fatter or skinnier, depending on where those numbers are. Now we're going to analyze gamma. This is no longer delta, this is gamma, and this is how this is going to affect delta as time passes. So gamma, this is gamma per strike. This is the at the money. This axis is the strike price. This is gamma per strike as the time to expiration changes. So when you're green, you have the longest time to expiration, and then black, less time to expiration, and then red, the least time to expiration, very close to expiration. So this is how gamma starts. Notice how it's concentrated near the at the money, because that's where the delta changes the most. But as time starts passing, that gamma starts going higher. Okay, so now if you look at the black one, this is taller and it's also skinnier. So these ones are no longer affected, the ones that are deep in the money or deep out of the money. When there's very little time to expiration, gamma is extremely high. Why? Because if you're near the at the money, at one point you're going to be switching between a delta of 0 at expiration and a delta of 1 at expiration. So it keeps switching back and forth. So gamma is very high because you're right in the border between delta 0 and delta 1, if you're talking about a call, for example. So this is a graph that's very similar to theta. Notice how the total area beneath or underneath the curve is the same as the one with the black one and as the one with the green one. So it's just distributed differently. In the case of the green one, with a long time to expiration, you don't have a lot of gamma because it's not that tall, but it affects more strikes, as you can see here, more options with strikes that are deeper in the money or out of the money. As time starts passing, those are no longer affected, but the ones in the middle, the ones right at the money, are going to be affected more. And then when there's barely any time left to expiration, gamma is going to be very significant and is going to affect the delta by a lot. And remember, delta can only go from 0 to 1. So it's not like gamma can take huge numbers. The gamma is limited because you can only switch delta from 0 to 1 or from 0 to -1 in the case of a long put. Okay, so that's why the graph for gamma has this basic shape. Now if we think about theta and gamma, how similar those graphs were, we notice that theta has a very similar graph, and this is the formula for theta. It's the same elements, just arranged in a different way. You have the standard normal distribution of D1, stock price, implied volatility, divided by 2 times the square root of time, and 365. This is the negative value because theta, if you're long an option, is going to affect you negatively. Okay, Gamma is what we saw, the standard normal distribution divided by the stock price, implied volatility, and the square root of time. So as you can see, theta, if you're talking about theta, it's dependent, it's directly proportional to the stock price and to implied volatility. In the case of gamma, it's inversely proportional to the stock price and to implied volatility. So if you have a very expensive underlying, the gamma is going to be less. In the case of theta, because the premium is going to be higher, theta has to be higher. Gamma can only move delta, and delta is bound by 0 and 1 or 0 and minus 1. Okay, so this is why implied volatility as well. If you have a high implied volatility, you're going to have a higher premium, but also the delta is going to be switching back and forth less. Okay, because remember when we talk about that graph, when you had a long time to expiration, which was the green one, the graph was short and fat. And in this case, having more implied volatility or time to expiration is going to achieve the same purpose. Okay, so it's going to be delta is going to be less affected by the moves in the underlying. So that's why gamma is less as implied volatility grows. Okay, so as we can see, we can get a relationship between gamma and theta. Okay, because we see that they're the same element. So what happens if we solve on both cases for the standard normal distribution of D1, which is what we're going to do. Standard distribution of D1, standard normal distribution of D1 is going to be minus theta multiplied by 730, which is 2 times 365, and the square root of time. So I'm moving this over here. Divided by, we move these two terms down. So we have the stock price and implied volatility. Okay. In the case of gamma, we isolate and we solve for n of D1. Same thing. It's going to be gamma times the stock price, implied volatility, square root of time. So because these are the same terms, we can have a new formula just using these two terms. Okay, so this is going to be minus theta 730 square root of time divided by stock price implied volatility. It's going to be equal to gamma stock price implied volatility square root of time. Okay, so if we solve for theta divided by gamma so that we can get the price that we're going to pay for every unit of gamma, okay, it's going to be the negative sign, and then we keep everything here. So stock price, sigma, implied volatility, square root of time. But then we have stock price and sigma as well here in the denominator. So we move it over here to the numerator, and we have stock price, implied volatility squared, square root of time divided by 730 times the square root of time. Okay, this is the same term, so it's going to go away, and we have now the theta divided by gamma. So what does this represent? We talked about gamma being very positive for option holders because it's an acceleration of profits and it's a deceleration of losses. To enjoy this advantage, you have to pay for it, and you're going to pay for it with theta, and theta is going to be related to gamma by this formula. What this means is that the price that you're going to pay to enjoy gamma, to enjoy 1 unit of gamma, is going to be obviously negative. So it's going to be a cost to you, and it's going to depend on the stock price squared and also implied volatility squared. And this is just a constant. So this is not even, this is just scaling it. So it doesn't even make sense to consider it. But if you think about it, if you have an expensive underlying, your cost per unit of gamma is going to be higher, okay? Because your theta is going to be higher because the premium is higher, okay? So the cost is going to be higher and in a square relationship. And also, if you have more implied volatility or higher implied volatility, then that premium is going to be higher. And so you're going to have to pay more theta and you're going to have the same gamma. So that's why it is directly proportional to the square of the stock price and the implied volatility squared as well. Okay, this is called alpha. Traders call this alpha or gamma rent. It's perhaps too much information for you. Probably not going to use it, but it's good to know that theta and gamma are two sides of the same coin. Now, we talked about gamma being the acceleration of profits or the acceleration of losses for those who have short positions in options. If we think about the delta gamma approximation, and we're going to have a lesson on this for advanced traders. We already have it, so you can check it out if you'd like. The delta gamma approximation is a formula that traders use to calculate how much the price of the option is going to be affected by all the different or the most important Greeks. So in this case, we'd be talking about what is the price of the option going to be if some of the parameters change. So the new price is going to be the old price plus the delta effect, which is the underlying price changing, plus the Vega effect, something that we haven't talked about, which is the effect of implied volatility changing, and also theta, which is what we already saw in the previous lesson. Okay, so the new price is going to be equal to the old price plus delta, but then the delta is going to be one at the beginning and one at the end of the price move. So you're gonna you're gonna take the average of those two prices to have the midpoint being the effective or the actual delta that's going to be affecting the new price of the option. So you're going to have delta plus the delta at the end, which is going to be delta plus gamma times the price change, which is what we talked about. Delta is going to be affected. Delta is going to change as price changes, as the underlying price changes by a factor of gamma. So delta plus gamma times price change divided by 2, which is the average of those two numbers, times the price change. And then Vega times the change in implied volatility. We haven't talked about this, but this is basically the formula. And then theta times the time elapsed. So theta is how much that option is going to go down by, and it's a negative number, times the time that elapsed. So if it was 1 day, this is going to be 1 because theta is a day, it's a daily number. Okay, so if we rearrange the factors here, you're going to have that the new price is going to be equal to the old price plus delta times the price change, which is the normal delta effect that we think about when we talk about delta. And then we're going to have 1/2 of gamma times the price change times price change, so it's price change squared, and then Vega and then theta. Let's not think about these two. We see that this factor, this 1/2 of gamma times the price change squared, this is how gamma is affecting your profits day by day. So this is how the P&L is affected by gamma. If you have a lot of gamma, then not only are you going to enjoy the delta times the price change, but you're going to have an additional portion that belongs to gamma. Okay. Now, in order, like I said, in order to enjoy these positive numbers, you're going to have to pay for them in the form of time elapsed. Okay. But this is going to be, if the move is big enough, this is going to cover those costs and then some. You're going to be left with a lot of profits. If it doesn't move, let's say, for example, the price didn't move, then delta is not going to act at all. Okay? So price change is going to be 0. So delta is not going to exist and gamma is not going to exist. So these two components depend on the price change. So you can see how gamma affects the P&L of a position by looking at the effect of gamma with respect to the price change squared, and 1/2 of that. That's going to be the effect of gamma. And as I said, if you're long options, you want movement and you want gamma acting and giving you profits. If you're short options, you don't want movement, so you don't want this gamma to act, because your gamma is going to be negative. So it's going to be leading to losses. Now let's go and take a look at the platform so that we can see an example of gamma actually in action. We're going to come to the platform and we're going to take a look at MasterCard. MA is a symbol, and I'm going to open up the 19th of June expiration. So we have 5 days to expiration. Okay. So what I'm going to do is I'm going to, well, last time for Theta, we thought about calls, and in this case, I'm going to go with puts. So I'm going to buy a put, and then I'm going to sell a put. Okay. So I'm going to go here to buy. So I'm going to buy the 297.79, 297.5. I'm buying the at the money put, okay? And I'm going to analyze this trade. So I'm going to be buying one of the 297.5 put with 5 days to go at 655, which is the price. So I'm going to put this price right here and this trade right here. I'm going to go back and I'm going to do the opposite. I'm going to be selling this put. So this trade, this one selling the put, is going to be bullish. The other one buying a put is bearish, of course. So I'm going to analyze this trade. So we have these two trades. In this case, I'm going to analyze 11 different prices of the underlying, and they're going to be changing by every 3% of the underlying price changing. Okay. So first we're going to look at buying a put. So buying a put, we already know that it's something like this. You pay the price 655, and then it hits the where the put is, and at expiration is going to start going in this direction. So the purple line is the line today, and at expiration is going to be this line. So if it goes down by a lot, you can make a lot of money. Okay, and you're going to lose a fixed amount. Okay, so I want you to focus on the delta. Okay, as the price is changing. Okay, when we buy the put, we're buying the 297.5, and the stock is trading at 297.79. The delta is minus 48. Now, what happens if the price goes to 288, which is this one, this point right here, okay, 288? Well, at that point, if it went in your favor by 3%, you're going to have more negative deltas, okay? So it's going to be even better because it's moving in your favor, and you have more of the thing that is making you profit, which is the deltas, the negative deltas. And if it goes even lower, it goes to 279, so another $9 down, then you're going to have an even better delta, okay, minus 87. And then if it's 270, which is right here when you already have a lot of money, because if it goes down by 9%, you already have, with putting down $655, you're going to be making at this point $2,018, so much more than you put in. When you sell options, you can only make the money that you put in, because that's the maximum profit for you. In this case, it keeps growing and growing, and the delta is moving in your favor by more and more and more. And why? Because here you have the gamma. Okay, the gamma is peaking right at the money, which is the point where you have the maximum gamma. Okay, and this is giving you extra delta. So if it moves, for example, from the at the money in your favor, and this move was $9, okay, so 9 times $2 going to be 18 deltas or so, but even more because it's 2.6, but even more because it's going to start with 48, and then the gamma at this point is going to be less. So we have to average these two and get an effective gamma acting on this whole path. But considering this is what's pushing the delta in your favor. Now, in the opposite direction, if it starts going against you, if it starts going higher, then you're going to have less and less delta, minus 26, minus 11, minus 4, such that you're never going to lose more than the money you put in. So right here, the delta is going to be almost 0. So you're not going to lose anymore. Okay, so this is how gamma works when you're long options, in this case a put. When you're short, it's a little bit different. This is a bullish position. When you start 297, which is at the money, you sell the option. If it starts going against you, which is down, minus 3, you have this delta at the beginning, 48 deltas, and now you have an even worse position. You have more deltas as it's going down, and then it keeps snowballing. So now you have 87 deltas at this point, which is 279 right here. Okay, 279 right here. You have 87 deltas. Okay, 87 positive deltas, and then 270 you have 96 deltas. So you're at this point you're basically long the stock. You almost have 100 deltas. You're 96, 99, 99. So at this point, you're pretty much long the stock. And if you go to expiration, you will be long the stock because you're going to be put that stock at the strike price, and you're gonna materialize the loss from here until to the point where the underlying price is. So as you can see, gamma is a friend to option holders and is an enemy to option sellers. That's the most important thing to understand about gamma. And gamma is an acceleration of profits for option holders, and it's an acceleration of losses for option sellers. This is the most important thing to understand about gamma, and I hope that it was clear. We've already looked at delta, theta, and gamma. We have only vega left, which is something that we're going to cover later on. But now you have 3 Greeks out of the 4 most important ones, and you should be able to analyze pretty much any position that you put on, which is a good thing because now you have a lot of positions that you can put on, and you can analyze them by looking at your Greeks and seeing, by the way, gamma for the same underlying can be added up, and that's going to be your total gamma. In the case of theta, for example, it is the same not only for any underlying price, but for any underlying for in your whole portfolio, period. So if you take the theta for Apple and Qualcomm and the spiders and diamonds, you just add them up and you're going to get your total theta. In the case of gamma, this is dependent on the underlying. So you can only add up the gammas for the same underlying, and you're going to get that underlying's gamma. Okay? Or that position, if you have a specific strategy, you just add the gammas for the position, and you're going to get the position gamma. So I hope that this was clear, and I hope that this concept is going to be useful for you in your trading, and I hope that this makes you a better option traders. As always, leave a comment if you'd like, and visit my website, which is optionsinplainenglish.com, where I have more material, something that could be useful for your option trading. Thank you very much, and goodbye.